Module 6, Chapter 3.7, Topics in Theory of Polynomial Functions, Part 2. Complex zeros. Solve the equation x squared plus 2x plus 4. Well, this one will not factor, so there are no rational solutions. But if we went through and did quadratic formula, a is 1, b is 2, c is 4, recall that would be negative b plus or minus the square root of b squared minus 4ac all over 2a. So we get negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 4 all over 2 times 1. So negative 2 plus or minus the square root of 4 minus 16 over 2, which is negative 2 plus or minus the square root of negative 12 over 2. Well, since the discriminant is a negative 12, we know we're looking at two imaginary solutions. Now we can simplify the square root of negative 12 as negative 1 times 4 times 3. The square root of negative 1 comes out as an I, the square root of 4 comes out as a 2, and the 3 stays in. So we get 2I square root of 3 over 2. Dividing everything by 2, we would get negative 1 plus or minus I square root of 3 over 1. Now, to enter this in my math lab, we're probably going to do negative 1 plus I square root of 3 and negative 1 minus I square root of 3. These are what we call imaginary solutions or complex zeros. We call the solutions of this type complex conjugates. Recall these are binomials where only the sign in the middle is different. Well, conjugate zeros theorem tells us if p of x is a polynomial having only real coefficients, and if a plus bi is a zero of the polynomial, then the conjugate a minus bi is also a zero. What that tells us is imaginary zeros always come in conjugate pairs. So we'll always have an even number of zeros. Recall the factoring method of solving a quadratic. You set it equal to 0, you factor, you set each factor equal to 0, and solve. Now, if we were to apply this in reverse, to find a polynomial when you are given the zeros, find the factors, multiply to get the polynomial. For example, find a polynomial having zeros of 4 and negative 1. Well, that means x is 4 and x is negative 1. Well, if the 0 is 4, then the factor was x minus 4. Or if x equals negative 1, the 0 was x plus 1. So if we multiply those together, we're going to get 0. So we get x squared plus 1x minus 4x minus 4. X squared minus 3x minus 4. Find a polynomial having zeros negative 9 and I. Well, if negative 9 is a 0, that means x equals negative 9 and x equals negative I. Well, if negative 9 is a 0, that means x plus 9 is a factor. If negative I is a 0, that means x plus I is a factor. And here's the missing part. Because negative I is a 0, positive I is also a 0. So if x plus I is a factor, x minus I will also be a factor. So I'm going to start out by multiplying those two, so we'd get x squared plus ix minus ix. Those two are going to cancel, minus I squared. But remember, I squared is negative 1, so this becomes x squared plus 1. And then we've got x plus 9, so multiplying that out gives us x to the third plus 9x squared plus 1x plus 9 equals 0. So our polynomial is going to be x to the third plus 9x squared plus 1x plus 9. Find a polynomial having zeros 3 and negative 4 that satisfies the requirement that p of 2 is equal to 4. Well, if 3 is a 0, x minus 3 is a factor. If negative 4 is a 0, x plus 4 is a factor. So p of x would be equal to this. Now, it also has to satisfy the requirement that p of 2 is 4, which means we're going to have some constant a out front. So we would get a times x squared plus 4x minus 3x minus 12. Or p of x is equal to a times x squared plus x minus 12. Well, if they tell us that p of 2 is 4, that means the function value is 4, and then x is 2, so that's 2 squared plus 2 minus 12. Well, that would give us a times 4 plus 2 is 6. 6 minus 12 is negative 6. Dividing both sides by negative 6 gives us a is negative 4 over 6, or negative 2/3. So our function becomes p of x is equal to negative 2/3 times x squared plus x minus 12. Or if we wanted to go one step further, negative 2/3 x squared minus 2/3 x. And then we've got negative 2/3 times 12, which would give us a positive 8. So this would be our polynomial. Find a polynomial having zeros 3, which would be x minus 3, and 2 plus I. Well, if 2 plus I is a 0, then 2 minus I is a 0. So we're going to have x minus 2 plus I, and we're going to have x minus 2 minus I. Well, let's simplify a little bit. This would be x minus 2 minus I, and this would be x minus 2 plus I. So if we group these two together, we would have x minus 2 squared. Outer 2 and inner 2 cancel out, and then we would get minus I squared. Well, minus I squared is the same as plus 1. So we would get x minus 2 squared plus 1, which is x squared minus 4x plus 4 plus 1, which is x squared minus 4x plus 5. Now that's times the x minus 3. So we get x to the third minus 3x squared minus 4x squared minus or plus 12x plus 5x minus 15. And so we would get x to the third minus 7x squared plus 17x minus 15. Now remember, this is times a, be equal to p of x. Now they're telling us x is negative 2, so we've got negative 2 to the third minus 7 times negative 2 squared plus 17 times negative 2 minus 15, and that's equal to 4. So on our calculator, we've got negative 2 to the third minus 7 times negative 2 squared plus 17 times negative 2 minus 15. And that would give us negative 85. So what we've got is a times negative 85 is equal to 4. Or dividing both sides by negative 85, we get a is equal to 4 over negative 85. So our polynomial function would be 4 over negative 85 times x to the third minus 7x squared plus 17x minus 15. And reduce that, but this is about what your polynomial function would be equal to. Now, a couple of theorems. The fundamental theorem of algebra says, every function defined by a polynomial of degree 1 or more has at least one complex zero. There's a number of zeros theorem that says a function defined by a polynomial of degree n has at most n distinct complex zeros. So, an example. For each polynomial, 1 0 is given. Find all remaining zeros. Now what that said was, if it's an x to the third, there are 3 zeros. Well, if we know one of them is 1, then we could do synthetic division by that 1 to reduce that. So that's 1x to the third, negative 5x squared, 17x minus 13. So drop your 1, that's negative 4, that's negative 4, that's 13, which we knew that was going to be a 0. Now we've got this one. Well, that would be x squared minus 4x plus 13 equals 0. We could do quadratic formula on that. A is 1, B is negative 4, C is 13. So that would be negative b plus or minus the square root of b squared minus 4ac all over 2a, which would be negative of negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 13 all over 2 times 1. Which would give us 4 plus or minus the square root of 16 minus 52 over 2, which would give us 4 plus or minus the square root of 36 over 2. Well, square root of negative 36 would be 6i. So we've got 4 plus or minus 6i over 2. Those all have a common factor of 2, so we get 2 plus or minus 3i over 1. So we were actually able to find them all. The first one is 1, then we have 2 plus 3i, and we have 2 minus 3i. Okay, let's do another one. For each polynomial, 1 0 is given, and they tell us that negative 5i is a 0. Negative 5i, there's our x to the fourth, x to the third, x squared, x, number. Negative 5i times 2 is negative 10i, which would give us negative 2 minus 10i. Now in the next piece, and we'll come over here, we've got negative 5i times negative 2 minus 10i. So that would be a positive 10i plus 50i squared. But 50i squared would be negative 50, so we've got negative 50 plus 10i. So that's negative 50 plus 10i. Now we can add our like terms together. 55 minus 50 would be 5 plus 10i. Now when we multiply this time, we've got negative 5i times 5 plus 10i. So that would be negative 25i minus 50i squared, but minus 50i squared would be plus 50, so we'd have 50 minus 25i. So this would be 50 minus 25i. So when we combine those, the negative 50 plus 50 cancel, so we get negative 25i. So now when we multiply negative 5i times negative 25i, we get 125i squared, which is 125 times negative 1, which is negative 125, which would combine, and that says, hey, negative 5i is a 0. So we're to this point. Well, because negative 5i is a 0, its conjugate would also be a 0, which would be 5i. So we're going to drop your 2. 5i times 2 would be 10i. Combine those and we would just get negative 2. Multiply this way would give us negative 10i. Combining those would give us just 5. Multiplying those would give us 25i squared. Combining those gives us 0. So there was one 0. There's a second 0. Now this would give us, if this was x to the 4th, this is x to the 3rd, so this is x to the 2nd. So this is 2x squared minus 2x plus 5 equals 0. So the question is, will that factor? Probably not. So let's do quadratic formula on it. Negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is 2, b is negative 2, and c is 5, which is 2 plus or minus the square root of negative 36 over 1 plus or minus 3i over 2. So our zeros would be negative 5i, positive 5i, 1 plus 3i over 2, and 1 minus. Now, the multiplicity of the 0 refers to the number of times that a 0 appears. Consider p of x equals x to the 6th plus x to the 5th minus x to the 4th minus x to the 3rd plus 8x squared minus 4x, which factors as x times x plus 2 squared times x minus 1 cubed. Now the factor x leads to a single 0, the number 0. The x plus 2 squared leads to a 0 of negative 2 with a multiplicity 2. And the x minus 1 to the 3rd leads to a 0 of 1 with a multiplicity of 3. If you'll think about this as factored form, that's x times x plus 2 times x plus 2 times x minus 1 times x minus 1 times x minus 1. And if you went through doing your 0 product property, this would give you 0, this would give you negative 2, negative 2, 1, 1, and 1, which remember we only have to write the zeros, we don't have to write them. But our theorem earlier said, hey, there's going to be 6 zeros, and looking at this we only see 3. But there's 1, 2, 3, 4, 5, 6. A function defined by a polynomial of degree n has exactly n complex zeros counting multiplicities. Okay, so if p of x equals x to the 4th minus 7x to the 3rd plus 18x squared minus 22x plus 12, and we want to find all of the zeros, then there's going to be 4 of them. Well, if 1 plus I is one of them, 1 plus I, then we're going to do 1, negative 7, 18, negative 22, and 12. So here we go. There's a 1. There's a 1 plus I, so that'd give us negative 6 plus I. Now if we multiply those two together, okay, so if we multiply those, we're going to get 1 plus I times negative 6 plus I, which is negative 6 plus 1I minus 6I plus I squared, but that I squared is negative 1, so we get negative 7 minus 5I. So if we combine like terms, we would get 11 minus 5I. So now if we did 11 minus 5i times 1 plus I, we get 11 plus 11i minus 5i minus 5i squared, which is going to make that a plus 5. So we'd get 16 plus 6i, which would give us negative 6 plus 6i. So now when we multiply that, we get 1 plus I times negative 6 plus 6i, which is negative 6 plus 6i minus 6i plus 6i squared, but that's going to become negative 6. So negative 6 and negative 6 is negative 12. 6i minus 6i cancel, so we get 0. But we expected that. Well, if that's 1, 0, then the next 0 would be the conjugate, which is 1 minus I. So 1 times 1 minus I would be 1 minus I. I's cancel, so we get negative 5. This would give us negative 5 plus 5i. I's cancel, so we get 6. This would give us 6 minus 6i. 6i's cancel. Negative 6 and 6 cancel, so this one is 0. So this would give us x squared minus 5x plus 6 equals 0. Now this one's going to factor x minus 2, x minus 3, so we get solutions of 2, 3, 1 plus I, and 1 minus I. Now, let's go the other way. Find a polynomial function of lowest possible degree with real coefficients having zeros of negative 3, 2, and I. Well, if negative 3 is a 0, x plus 3 is a factor. If 2 is a 0, x minus 2 is a factor. If I is a 0, then x minus I. And if I is a 0, then we must also include its conjugate, which is negative I, which would be x plus I. So if we were to multiply this out, the first two together would give us x squared plus x minus 6. The last two together would give us x squared, outers and inners cancel, minus I squared, but that's going to be plus 1. So from there we would get x to the 4th plus x to the 2nd plus x to the 3rd plus x minus 6x squared minus 6, or rearranging x to the 4th plus x to the 3rd minus 5x to the 2nd plus x minus 6. And this would be our polynomial function. Now, find a polynomial function of lowest degree with real coefficients having a 0, 2 of multiplicity 3. Well, if the 0 is 2, then x minus 2 is a factor of multiplicity 3, means it's going to occur 3 times. Having a 0, 0 means the factor would just be x of multiplicity 2, means it's squared. And having a 0 of I means we're going to do x minus I. Then it says of a single multiplicity. Well, that would be 1, but remember, its conjugate must also be in there. So this would be our function. Now, the behavior at zeros. Graph the following functions and observe the behavior around the zeros of polynomials. Okay, if we take the first polynomial, x plus 3 times x minus 2 squared. Now in this one, we know that the zeros are going to be at negative 3 and positive 2. But if we graph it, what you'll notice is it crosses at negative 3, but it only touches at 2. So I'm going to stick a little C for crosses and a T for touch. Now, if we change that around a little bit and we call this one x plus 3, and let's insert a squared on that one, and we do x minus 2, and let's change that to a power of 3. When we graph that one, now it touches at the negative 3, and it actually crosses at the 2. You see the pattern yet? Let's do it one more. X plus 3, we're going to say up arrow, and I'm going to insert my third power, times x minus 2, and we're going to change that one to the 4th. What happens on that one is it goes back to crossing at x plus 3, and it goes back to touching at 2. What you're going to find out is anytime the multiplicity is odd, the graph is going to cross at that 0. And anytime the multiplicity is even, the graph is going to touch at that 0. Okay, so in conclusion, the graph crosses the x-axis at C if C is a 0 of odd multiplicity. The graph is tangent or touches in one place. It's tangent to the x-axis at C if C is a 0 of even multiplicity. That is, the graph will touch the x-axis, but it will not cross it. The graph becomes flatter at C as the multiplicity of C increases. So the more there are, the more leveled out it would be at that point. Now, by observing the dominating term and noting the multiplicities of zeros, we can draw a rough graph of a polynomial by hand. So, looking at this, we know that the degree would be x to the second times an x squared. So there's an x squared, another x, and an x squared. So we know that the degree of this one is going to be 5. Okay? So remember, x to the odd power, the graph looks like this. But an odd power with a leading coefficient of -2 flips it, so the graph would look like this. Okay? So this is an odd power with a negative coefficient. So that's sort of what we have. Now, if x plus 4 is a factor, -4 is a 0. If x plus 3 is a factor, -3 is a 0. And if x minus 1 is a factor, 1 is a 0. So, we're going to look at this one. We know the graph starts up here, and we know it ends down here. X plus 4 squared means the graph is going to come down here, touch it at -4, and then bounce back up. X plus 3, now that's an odd power, so that means it's going to cross it. So it's going to come back down here, and it's going to cross at -3. Now at x minus 1, that's an even power, so it's going to touch it. So it's going to come back up to 1. It's not going to cross, but it's going to come back down, and that puts us in our general direction. So our graph would look something like this right here. Let's do another one. The 0 would be -1, -4, and 2. Sorry. Odd power means it crosses here. Even power means it touches here. Odd power means it crosses here. Leading coefficient is positive, and the degree is the sum of all of our exponents. So there's an x to the third, an x to the second, so there's 5 x's, and one more would be 6. So if it's an x to the 6, we know they're both up or both down. A positive coefficient means they're both up. So that's sort of what we're shooting for. So at -1, -4, and +2. So it starts up, it comes down here to -4, touches it, comes back up, -1, crosses it, comes over to x minus 2, crosses it, so that gets both of our end directions up. Now the rational zeros theorem says, let P of x be of that general form if P over Q is a rational number written in lowest terms, and P over Q is a 0 of P, then P is a factor of the constant term a sub 0, and Q is a factor of the leading coefficient a sub n. So what that says is all possible rational solutions, or possible rational zeros, have to be of the form factors of a sub 0 divided by factors of a sub n. So it's factors of a sub 0 over factors of a sub n. These are the only possibilities that we're going to have for solutions, or zeros. So the first example says list all possible rational zeros. Well, factors of 2 are positive or -1 or positive or -2. Factors of the leading coefficient would be positive or -1, positive or -2, positive or -3, and positive or -6. So I'm just going to say positive or negative. 1 over 1 is 1. 2 over 1 is 2. 1 over 1, 2 over 1. 1 over 2 would be 1/2. 2 over 2 would be 1, but we've already got that one listed. 1 over 3 would be 1/3. 2 over 3 would be 2/3. 1 over 6 would be 1/6 listed. So these are the only possible rational zeros that we would have to consider. Now, the question says, find all rational zeros and factor P of x. Well, we know there's at most 4 solutions. So what we would do is we would take, let's start with our nice pretty ones. Let's try 1 into 6, 7, -12, -3, 2. So if we drop our 6, 13, 13, 1, 1, -2, -2, 0. 1 is a solution. Okay? Now, what we can do now is we can consider this new 6x to the third plus 13x squared minus 1x minus 2. But you know what? We're still going to have 2 over 6's, so we're still going to have the same list of possible zeros. Okay? Let's try 1. 1 could be a multiplicity 2. Let's try 1 again. 6. That would be 6. That would be 19. I think we're going in the wrong direction. 19, 20, 20. So 1 did not work again. Okay? Let's go back to 6, 13, 1, -2. Let's try 2. Drop your 6. 6 times 2 is 12. 25, 50. We're going the wrong direction there. Let's try -2. 6, 13, 1, -2. Drop your 6. There's -12. There's 1. There's -2. There's -1. There's 2. There's 0. Hey, we found another one. So we found 2. Once you get it down to quadratic, remember this first one was an x to the 4th, which means this one was an x to the 3rd, which means this one's going to be an x to the 2nd. So what we've got is we've got 6x squared plus x minus 1 equals 0. Well, that factor 3x and 2x minus 1 plus 1, that'd give us a positive 3 and a -2. So that says that this factor would be 1/3, and this factor would be -1/2. So our zeros would be 1, -2, 1/3, and 1/2. Factoring, well, if 1 is a 0, x minus 1 is a factor. If -2 is a 0, x plus 2 is a factor. X minus 1/3 and x minus 1/2. And knowing that x times x times x times x would be x to the 4th, and we needed a 6x to the 4th, then we would put a 6 out front, and this would be our answer. Now, there's a boundedness theorem that shows how the bottom row of synthetic division is used to place upper and lower bounds on possible real zeros of a polynomial function. It says is, let p of x define a polynomial function with degree n greater than or equal to 1, with real coefficients and with a positive leading coefficient. If p of x is divided synthetically by x minus c, and if c is greater than 0, and all numbers in the bottom row of the synthetic division are non-negative, then p of x has no 0 greater than c. Or, if c is less than 0, and the numbers in the bottom row of the synthetic division alternate in sign, with 0 considered positive or negative as needed, then p of x has no 0 less than c. So what it says is, if you are doing synthetic division by a positive number, and the bottom row of synthetic division are not negative, then you found an upper bound. There's no 0 greater than the number you divided by. Or if you're dividing by a negative number, and the numbers in the bottom row alternate, then you have found a lower bound. Okay, let's practice. Show that the real zeros of p of x satisfy the following condition. If you are showing that no real 0 is greater than 3, that means we're doing synthetic division by 3. So that's 2, -5. There's no x squared, so we'll put in a 0, 3, and 1. So if we drop your 2, there's a 6, there's a 1, there's a 3, there's a 3, there's a 9, there's a 12, there's a 36, and there's a 37. All of these are non-negative, which means we have found an upper bound. There will be no real 0 greater than 3. If we do for -1, 2, -5, there's no x squared, 3x, and 1. We drop our 2, so that would be -2, that's a -7. That would be a 7, that would be a -7, so that's a -4, that would be a 4, and that would be a 5. So because we did synthetic by a negative number, and we got positive, negative, positive, negative, positive, that means that -1 is a lower bound, so we don't have to try any numbers less than a -1. You are now ready to complete this section of homework on my MathLab.